Now, if we wanted to make more accurate predictions, we would need to increase the number of intervals that we were using. And that would increase the amount of addition I had to do and make it a little more tedious. And that's where summation notation or sigma notation is going to come into play. We're going to use the Greek letter sigma, capital sigma, to stand for sum. It doesn't look like an S to us, but it's the Greek S, so that's why we're using it. It's S for sum, and it's been in use for a long time. So sigma S is going to stand for sum, and to write a sum, like 1 plus 2 plus 3, etc., plus 10, we can simply say that we're going to add up k values from 1 to 10, and we're adding up the k. So k is called the index, and it takes on only integer values from the lower limit through the upper limit. So we have to look at our lower limit and our upper limit, and then the argument, the summand, in the summand is the expression in terms of the index that follows the sigma. It's the thing you're adding, the k. And it can be evaluated for each value of k to find the sum. So in this case, the summand was just k. Okay, now on a calculator or Desmos, we're going to look at both. We can use summation notation to add something up. Okay, so we're going to do that a couple times. So first, write the first two and last two terms of the following sum and then evaluate them. All right. So first, for k equals 1, this is going to be 2 times 1 is 2. I'll just write 2 times 1. For k equals 2, we would have 2 times 2. And then the last two, for 3 and 4, I'd have 2 times 3, and I would have 2 times 4. So I'm just adding up 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. If I do this one by hand, I'm going to make sure that I know the sum matches what I get from sigma notation. So this is the same as 2 plus 4 plus 6 plus 8, so that's 20. Okay, now if we check this in summation notation, I do have a calculator. I can do it on the calculator first, but we're going to do most things in Desmos. But since it does mention the calculator, if you prefer using this thing, it's fine. So if you go into math and then up to get to the bottom of it, summation notation is option 0, and you have to type in what letter you want to use. It doesn't really matter if it's K or A or whatever, but it's already in alpha, so I'm looking for K. Where it is, there it is. And it's k equals 1, 2, 4, and then 2k, alpha k, is what I'm adding. So I get 20. All right, so let's check it out in Desmos instead. Same thing. Okay, so in Desmos, if you go into the tool palette and functions, in miscellaneous, we can get into some sigma notation there. And so n, they call it n by default. You can change it to k if you like the letter k instead. Sometimes we use n, sometimes we use k, sometimes we use both, which is why I like to keep it k, because n usually goes on the top if I use both. Doesn't matter though. And then 2k. 20. Perfect. Now, if you don't like having to click through menus to find that, you can also just type sum, S-U-M. Boom, pops into sigma notation, and we can just illustrate again that you can do it with any letter and replace n's and k's, and boom, you got the same thing. So, easier to do it in Desmos than having to go through menus in the calculator, I believe, especially if you can just type S-U-M, sum, and you got your sigma notation popping right up. Summation notation or sigma notation. So, first one's 20. Let's check out some of the other ones. This one's k squared. Only 4 terms again, so I'm adding up 1 squared plus 2 squared plus 3 squared plus 4 squared. If I tried this by hand, I'm adding 1 plus 4 plus 9 plus 16. That's 10 plus 20. That should be 30. And verify. If we do the sum from k equals 1 to 4 of k squared, it's 30. Excellent. So we get 30. Now I won't add the other ones by hand, we'll just use the summation notation to add them up. And so this one is of 3k squared. Okay, so those terms would be 3 times 1 squared plus etc. plus 3 times 4 squared. Okay, so that sum is 90, which I am not surprised by. We're going to get a property about that in a second, but well, first we'll do the last one. So this one would be 3 times 1 squared plus 2 times 1 plus etc. plus 3 times 4 squared plus 2 times 4. Oh, I'm sorry guys, this one was still up. But we're just plugging in 1 for our k's, plus then you would do 2 and 3, and then finally 4. And so if I go back to decimals now, I'm going to throw in some parentheses just to make sure that this all lands inside the summation. Plus 2k, and we get 110. Okay, now noting that my paper, noting that if I knew what the sum of k was, it's 30. The sum of k squared, I meant to say. The sum of 3 times k squared, 3 times 30, 90. Not surprising. So that conclusion leads us to a conclusion here for if you want to do the sum from, it doesn't matter if it's k equals 0 to n or k equals 1 to n, it's just a index start. We use zeros and ones depending on what we're doing. You'll do more on summations and series in Calc 2. But it's going to be the c factors out, and it's c times the sum from k equals 0 to n of a sub k. Okay, so you can do the sum and then multiply by the 3 afterwards. It's just like factoring the 3 out. And then if we did the sum of 3k squared, we got 90. The sum of 2k, you got 20. 90 plus 20 is 110. So no surprise, this one came out to be 110. So if two sums exist, you can do the two sums separately. So this would be broken down into the sum k equals 0 to n of a sub k plus the sum k equals 0 to n of b sub k. You can do the two sums separately or together, depending on which one is more advantageous. All right. And on our next page, as with other shorthand notations, there are some useful patterns of summation notation that can be used in the event of need for algebraic manipulation. Okay, so I want to start to practice writing things that are not in sigma notation in sigma notation. So these are sums that I want to fill into sigma notation. So I'm going to start with a k equals 1 value, and I want to know how many times to add it. So I'm just going to count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 items there. So I want k equals 1 to 10. Now what am I adding each time? The thing that I'm adding each time is a sum end. So I'm adding 3 each time. So the sum from k equals 1 to 10 of 3 is going to match this list. Okay. Looking at the next one, there are 1, 2, 3, 4, 5, 6, 7 things that I'm adding, and what I'm adding is changing each time. The first one, I add 1. The second one, I add 2. The third one, I add 3. The last one, I add 7. So making a list of k values, the number of the item, it matches exactly. So what I'm adding each time is k. Okay, that's a handy technique, is to number them. So here it was 1, 2, like the third term, the fourth term, they were all the same. The 10th term, they were all the same. They were all 3. But here they changed. They were the k value that I was adding. So the sum from 1 equals 7, from k equals 1 to 7 of k. In the next one, I'm adding k equals 1, 2, hold on, 1, 2, I'll also number them, 1, 2, 3, 4, 5, 6. Numbering them is especially helpful in finding the patterns. There are 6 of them, so I'm going to 6. And what am I adding? In terms of the k value, those numbers are k squared. So we're adding k squared. Okay, number these again, 1, 2, 3, 4. There are 4 things that we're adding, so sum from k equals 1 to 4. What is it? It looks like k cubed. And the next one, we're adding 1, 2, 3, 4, 5, 6, 7 things. So k equals 1 to 7. And the pattern looks like 5 times the k value. So we're adding sum ends of 5k. Once you see the k values, you can see the pattern that goes between the k values and the number. Then we have 1, 2, 3, 4. So k equals 1 to 4. Okay, this one's a little trickier because I don't see a relationship directly between 1 and 2, 2 and 16, 3 and 54. 4 and 128. They are very large, but I don't think it's growing exponentially. I think it is growing in a cubic type pattern. Notice that if I have my cubes, they are similar, but if I doubled them, boom, I have my cubes. So this is a pattern of 2 times k cubed. It's not just k cubed. If there's a constant multiple or even an addend, it gets even trickier to find those patterns. So that's something that you'll practice as you continue into Calc 2 as well. So there we go. Our pattern for that one is 2k cubed. Now there are some basic summation rules that allow us to by hand simplify some of the basics. So like the sum of a constant. If you're adding up a constant n times, that sum is c times n. If you're adding up k n times, that sum is n plus 1 times n over 2. If you're adding up k squared, there's a pattern for that sum. You can always add it up, and if you're adding up k cubed, there's a pattern for that one as well. So we're going to check these patterns out as well as evaluate. By the way, we didn't do that yet. These did ask us to evaluate as well. So they asked us to get them in summation notation and evaluate. I'm going to go back and do the evaluate step. Just want to mention these. This one for the bottom, the Cn, matches up with this top one here. It says that the sum should be equal to 3 times n. So 3 times 10. This sum should be 30. Okay. This one says that the sum should be n, which is 7, times n plus 1, which is 8, divided by 2. That's a sum of k. And so that's going to be 4 times 7 is 28. This one says that n is 6, so this should be 6 times n plus 1, which is 7, times 2n plus 1. 2n is 12, plus 1 is 13, divided by 6. And I don't know what the product of 7 and 13 is, so let's find out. 7 times 13 is, this one should be 91. Okay. We could do something similar for the rest of them. I'm going to pause right here, and we're going to get these evaluated on Desmos and check the ones we already did, and then get the other 3 that way. Okay, so we're going to do the sum from, I'm going to make it a k just for fun. K equals 1 to 10 of 3. It's 30, not surprised. Now if we just go to 7 and we add up k instead, 28. That matches what we said for b. If we add up k squared instead, but we only go to a 6, we get 91, which does match what we had there as well. And now for the other ones, I'm going to go to 4. Now it's going to be k cubed. And so we get 100. So the next one is 100. Just writing down our 100 here, and we're going to do the last 2. And I'll flip my screen back over there. So this one is k equals 1 to 7, and it is 5k, and so I get 140. And then 2k cubed, but we're only going up to 4, and so we get 200. And so, again, those 3, which I didn't find with the patterns, you could find with the patterns as well. The patterns work. We don't really have patterns for other types of functions besides these couple power functions, the linear term, the quadratic term, and the cubic term, although you could add up multiples of these. You could combine these rules as well, the constant multiple rule times the, if you had some add-ins as well, you could combine those rules to get any polynomial function.